Today my talk is about coupling of graphene nanoribbons to lengthen and illuminate strontium titanate electron waveguides via nanoscale vias. The second quantum revolution of the 21st century is based on the utilization of interesting quantum phenomena like quantum entanglement and quantum superposition, and aims to develop revolutionary technologies such as quantum computers and simulators. In our group, we are interested in developing the physical foundation of future quantum technologies like spin-based quantum computers. A big challenge that we face is trying to meet all the stringent requirements that any quantum computing platform needs to satisfy, such as the ability to coherently control and measure individual qubits. Graphene nanoribbons, or GNRs, emerge as a promising electronic material with many interesting electronic properties, including topological quantum states and a highly tunable energy band gap that depends on the structural design of GNR and can be controlled during the chemical synthesis. GNRs have recently been proposed as a promising candidate to host a new family of spin qubits. A big milestone in reaching this goal is to be able to have direct electrical contact and apply gate voltages to individual GNRs. We can apply a transverse electric field to a metallic GNR that will open an energy band gap, leading to the formation of a topologically protected electron state. The main material platform that we study in our group and we use to host other quantum materials is lanthanum illuminate strontium titanate heterostructure, which was shown to have a locally switchable metal-insulator transition at the interface, with the condition of the lanthanum illuminate layer being about 3 unit cells, which is about 1 nanometer in thickness. What we do to create nanostructures is that we first create metal electrodes that contact the interface. Then we use a conductive AFM tip that's biased with respect to the interface to sketch the device around. And what happens is that wherever the tip touches the surface, underneath the surface becomes locally conductive. And this is reversible in the sense that we can change the sign of the voltage and revert to an insulating phase. Using this technique, we can create lots of interesting quantum devices with very high spatial resolution of about 2 nanometers. Another technique for writing nanostructures on lanthanum illuminate strontium titanate that has been developed recently is ultra-low voltage e-beam lithography. Here we replace the biased AFM tip with an electron beam to sketch the device. The interface below the exposed region becomes locally conductive. We use low acceleration voltage of about 100 volts to avoid causing physical deformation to the sample. Compared to the conductive AFM lithography technique, this technique offers much higher writing speeds that can reach 10 millimeters per second, which makes it more convenient for creating large two-dimensional devices. This technique also allows for writing through stacks of two-dimensional materials. Over the years and using this technique, it was possible to create a variety of interesting nano-electronic devices, including field effect transistors, photodetectors, and also working with other materials like monolayer graphene, and we were able to explore and discover many interesting physical phenomena. We also use atomic force microscopy to transfer GNRs to the location of interest on the lanthanum illuminate strontium titanate samples. The way we do this is that we start with a GNR powder that's provided by our collaborators. We place it on the lanthanum illuminate surface. Then we bring an AFM tip in contact with that region, and what happens is that the tip starts to pick up a small number of GNRs. Next, the tip is moved to the location of interest on the lanthanum illuminate surface, and while scanning in contact mode, the tip starts shedding GNRs. Finally, the tip is removed and replaced with a clean one, which is used to image the surface as well as patterning nanostructures with conductive AFM lithography. To improve the electronic coupling of GNRs to lanthanum aluminate strontium titanate, we thought to bring them closer to the conductive interface by pushing individual GNRs into a nanovia, which is a nanometer scale hole where the lanthanum aluminate is removed. We found that in some of our samples there are some naturally occurring holes with sizes of about 200 nanometer, which is too large compared to the sizes of individual GNRs and other quantum dots. For that reason, we thought to artificially create these nanovias where we can control their locations as well as their sizes. The way we create these nanovias is using low voltage e-beam lithography. We use the low acceleration voltage of about 1.7 kilovolts because our samples are highly insulating and high energy electrons causes deformation to the sample in the form of physical damage when the electrons stop in the bulk of the STO, and that might cause it to become permanently conductive. Using low acceleration voltage also requires us to use very low charge dose, as the cross-section of the electrons is much higher at lower voltages. And we can see that clearly in Monte Carlo simulation of the electron trajectories inside the e-beam resist layer. So we start with a regular STO sample with 1.2 nanometer lanthanum aluminate layer on top. Then we spin coat polymethyl methacrylate or PMMA as an e-beam resist layer. Next, we pattern the resist with our nanovias using a scanning electron microscope. Then we develop the PMMA to remove the exposed regions of the resist and to transfer the nanovia pattern from the PMMA layer to the lanthanum aluminate layer. We use argon ion milling, where the remaining PMMA acts as a mask to protect the LaO surface. And finally, we remove the PMMA layer with acetone. Once we create these nanovias, we then create metal electrodes that contact the interface. Then we can transfer GNRs or any other desired material and perform direct electrical measurement on them. So far, we managed to bring the sizes of these nanovias down to 50 nanometer. The depth of these holes range between 1.5 and 2.5 nanometer, which is less than 1 nanometer below the interface. We also managed to create metal interface electrodes and wire bonding pads around the regions containing these nanovias in our sample. What we are trying to do next is to place an individual GNR inside one of these nanovias and make direct electrical contact to it. We will start with a simple 4-terminal device, and once that is established, we can move forward and create more advanced nanoelectronic devices, such as single electron transistors, where we can use a GNR as the quantum dot and use that device to probe the electronic structure of GNRs. We are also very excited about trying to couple other nanomaterials with the conductive interface using the nanovias, like cadmium selenide, cadmium sulfide nanoparticles, for example. To summarize, we are interested in realizing a new type of spin qubits based on graphene nanoribbons. We want to electronically couple GNRs to LaO-STO conductive interface. We do that by creating nanovias in the lanthanum aluminate layer with low voltage EBL, and then transfer individual GNRs inside using atomic force microscopy and perform a 4-terminal GNR measurement, and in the future create a GNR SET. Thank you.